Hello everyone, welcome to DrZ Academy. In today's video, we're going to talk about Poisson distribution. Let's start. Okay, so now what is a Poisson distribution? Consider this definition. A random variable x is said to be a Poisson random variable with parameter lambda greater than 0 if its probability mass function is given below. Alright, so the p of x equals lambda to the power x over x factorial e to the power negative lambda. Right, so here x can be 0, 1, 2, and so on. So lambda here is the Poisson parameter. Okay, so Poisson distribution is a very important probability distribution. It appears in the exam P constantly, right? So almost every exam you take, there is a Poisson distribution. Okay, so very important one. Now, for this Poisson distribution, we have the following theorem, right? Let x be a Poisson random variable with the parameter lambda, then the moment generating function is going to be what? Given below here, right? It equals this one. Now let's just prove this theorem, right? It's a very simple proof. Okay, moment generating function of t, as we know, is e to the power expectation, e to the power tx, all right, so which equals the summation over x. Now x can be 0 to infinity, all right, so as you can see, it is from 0, 1, 2 till infinity, right? So now here is e to the power t of x, all right, times the p of x, so which is what? Lambda raised to the power x over x factorial e to the power negative lambda. All right, so then you can see that this one equals x equal to 0 to infinity, and you can put this e to the power tx, lambda x, put them together, so lambda e to the power t raised to the power x over x factorial e to the power negative lambda. Right, so e to the power negative lambda, and this is actually a constant with respect to x. So you can take the e to the power negative lambda to the front, and in the summation here is x equal to 0 to infinity. So lambda e to the power t raised to the power x over x factorial. Now this is actually what? The Taylor expansion of the function e to the power, right, lambda e t times, right, so that's just e to the power lambda e to lambda et, right? So now therefore we can see that this is actually equals what? E to the power lambda et minus lambda, which is e to the power lambda e to the power t minus 1. Okay, so that's what we have, right? That's what we have. Very good. All right, so this is the moment generating function of this Poisson distribution. Okay, so with this moment generating function, we can get the expectation and the variance, right? So now, for instance, since moment generating function of t equals what? E to the power lambda e to the power t minus 1, right? So then the first derivative, so is what? Firstly find it using chain rule, right? So this is going to be lambda et e to the power lambda et minus 1, right? So then you can just put them together, lambda e to the power lambda et plus t minus lambda, right? So this is going to be the first derivative. And then the second derivative is the derivative of the first derivative. Yes. So now, again, chain rule, lambda times lambda e to the power t plus 1, right? Plus 1. Okay, and then e to the power lambda et plus t minus lambda. All right, so that's going to be the second derivative. So we know that expectation of x is going to be what? The value of the moment general function, the first derivative at point 0, right? So you can see that when t is 0, so this exponent is 0, right? So lambda minus lambda, 0. So therefore it's lambda, right? And then we can also find the expectation of x squared. The second moment is the value of the second derivative at point what? 0, right? So here's x at point 0. So when t equal to 0, so you have lambda, and this is lambda plus 1, right? And t is 0, so this is going to be just 1, right? So therefore, this one equals what? Lambda squared plus lambda, right? This is the expectation of the second moment, all right? So, and then the variance of x is going to be what? Expectation of x squared minus the square of the expectation, right? So that's what we have. So this one is going to be what? Lambda squared plus lambda minus what? Lambda squared, so which is lambda. Therefore, the expectation is lambda, the variance is also lambda, right? So we got this theorem proved. Yes, if x has a Poisson distribution with parameter lambda, then expectation and the variance are both lambda. Very good. Okay, so let's consider this example. The number of phone calls to a front desk at a hotel average at 3.2 every 10 minutes. Average at 3.2 every 10 minutes. All right, so assuming that a Poisson distribution is appropriate. Okay, so what is the probability that the 4 calls will occur in a 10-minute period? Okay, so let's consider this one solution. Now let's first define our random variable be the number of phone calls. All right. So in a 10-minute period, in this 10-minute period, okay. So now then, assuming Poisson distribution and also the average at 3.2, right? So then expectation of x equals what? 3.2. Okay, that's the average, right? The 3.2. Okay, so expectation is 3.2. Now, since it is a Poisson distribution, since x has a Poisson distribution, right? So we know that lambda what equals the expectation of x, which is what? 3.2, right? So that is to say x has a Poisson distribution with parameter lambda, which is 3.2, right? So sometimes we use the notation, right? So x has sometimes you can just write down in this Poisson lambda. All right, Poisson lambda. This will be tells us it is a Poisson, right? Hence, the distribution x has a Poisson. All right, so lambda is 3.2. Okay, so that's going to be the distribution of the random variable x. Now, what is the probability that 4 calls will occur in the 10-minute period? So that is to say probability what? X equals 4, right? So which is p of 4. Now, since lambda equals 3.2, so this is 3.2 raised to power 4, right? Raised to power 4, 4 factorial e to the power negative 3.2. All right, so let's calculate this value using this one, right? So, all right, let me see. Okay, Okay, here we go. 3.2 raised to power 4 over 4 factorial in the parentheses 4 proper parentheses. Okay, and then you multiply e to the power second e to the power negative 3.2. Close the parentheses. All right, so I got this one is 0.1781 if you round to 4 decimal places. All right, so that's what we get for this example. All right, so here it tells you the average. That is going to be our expectation. Now, because it has a Poisson distribution, the lambda, the parameter, is just the expectation. So you got to know that, right? So for Poisson distribution, the expectation equals the variance equals lambda, right? So since the average is 3.2, so lambda is 3.2. Now then you need to know the PMF of Poisson distribution, right? So for Poisson distribution, the it's what? Lambda to the power x over x factorial e to the power negative lambda. Remember? Right? So this is the PMF. So therefore just P4, that's just plugging x equal to 4 there. So we found that this probability is 0.1781. Okay, so that is this example. All right, so very good. Now let's consider another one, right? So let's consider another one here. So say that the number of auto insurances sold by a salesman per week has a Poisson distribution. All right, so the number of auto insurances sold by a salesman per week has a Poisson distribution. If the probability of selling none in a week is 1 over 10,000. All right, so find the probability of selling 4 or more auto insurances in a week. Okay, so again, here solution, right? So you can do this. All right, so let's define our x be the number of auto insurances sold sold per week. Sold in a week. Sold in a week. All right, so then x has a Poisson distribution. Then x has a Poisson distribution, lambda, right? So with parameter per lambda, where lambda is unknown, right? So we want to find the lambda, right? Here, where lambda is definitely greater than 0, okay? So now, since what? The probability of selling none in a week is 1 over 10,000. So we know hence, all right, P of 0 equals what? Lambda raised to power 0 over 0 factorial e to the power negative lambda equals what? 1 over 10,000. All right, so now you can see that this implies you can solve this one, right? So lambda equals what? So this is 1, all right? So e to the power lambda is 1,000. Lambda is actually ln 10,000, right? Actually, lambda is ln 10,000, okay? So you can just leave it like that, all right? So ln 10,000. Right, lambda is ln 10,000. And we want to find the probability of selling 4 or more, right? Okay, so 4 or more. Okay, so what you can do is probability for x greater or equal than 4, right? So which equals what? Now you may want to do is 1 minus the probability using the complement or less than 4, right? So less than 4. So it equals what? If it is less than 4, it means 1 minus either 0, 1, 2, 3, right? P of 0 minus P of 1 minus P of 2 minus P of 3, right? So which equals 1 minus, right, P of 0 is going to be, as we see here, right? So it's 1 over 10,000. All right, so we already got this one. Minus P of 1 is lambda, right? Ln 10,000 over 1 factorial e to the power negative lambda e to the power negative lambda is 1 over 10,000. Okay, so it's 1 over 10,000, right? Minus 2 is ln 10,000 square over 2 factorial times 1 over 10,000 and minus, all right, so ln 10,000 and to the power 3 over 3 factorial 1 over 10,000. Okay, so which equals what? Okay, so you can just do this one, right? So let me just use a calculator to find this one. 1 minus 1 over, oh gosh, 10,000. All right, minus ln 10,000 over 10,000 minus parentheses ln 10,000 close the parentheses and close and square, right? Square over 2 and over 10,000 and then minus parentheses ln 10,000 close the parentheses raised to the power 3 over 6 over 10,000. All right, so let's see. Okay, so this one I got this 0.9817. All right, 0.9817. So that's going to be the probability. Yes, so you got to be careful in the calculation, right? Especially the calculator. That's kind of complicated, but just be very careful. So this is going to be this example, right? So we firstly define our random variable, and then got this Poisson distribution, and then with the PMF, right? So with the given information, we can solve for lambda. After we got the value for lambda, so we can find the probability of selling 4 or more, right? So using the complement rule. So it's better to use the complement rule here because greater or equal to 4, that can be 4, 5, 6, 7 till infinity, right? So probably it's better to do this one, 1 minus that, right? That's a lot better. Okay, so I think that's all about this this video, and thank you so much for watching. And if you feel like this video is helpful, please click on the like button. If you think this video will benefit some of your friends, please feel free to share it with them. And as always, thank you very much, and I will see you in the next one. Bye bye.